In this example, we've got the same car moving with increasing velocity over the same 10-second interval. Only now we are sampling the velocity every second and instead of every 2 seconds. And so we have a table of data. And I've taken the liberty to go ahead and plot that data so you can see the curve. And then I've drawn in the rectangles representing the left-hand sum. So basically I've taken the left-hand data point over each 1 second interval and use that. We're going to use that as the height of the rectangle for each of these areas, right? We're just going to take the height of the rectangle times its width and then add up all the areas of those rectangles. Okay, so basically what I'm doing is I'm just gonna take these first few data points, except for the last one. Now in this case, we have 11 data points because we have 0 through 10. But in this case, our delta t is equal to 1, and our n is equal to 10 because we have 10 time intervals. All right, so we're just going to take these first 10 velocities and use them as the height of the rectangles for our left-hand sum. So left-hand sum. All right, so let's compute that left-hand sum. So the left-hand sum is going to be, now I can just factor out the 1, right? That they're each a width of 1. So, each interval is going to be something times 1. So I'll just factor out that 1. So really all I need to do is just add up those data points. 20 plus 25 plus 30 and so on, all the way down to the second to the last value, right? 49 is going to be my last value because it's my last left-hand data point. All right, so I just add those all up and multiply by 1, and I got 371 feet. All right. So now let's do the same thing and get a right-hand sum. So again, I should mention that this is going to be an underestimate, right? You could tell just from the graph, all of these areas that I'm adding up are all below the curve, and so this is going to be an underestimate. All right, so let's try the right-hand sum. So I'm going to draw in all those rectangles. So instead of using the left-hand data point, I'm using the right-hand data point to approximate the area of each rectangle. Okay, so that's what I'm going to do. So for the right-hand sum, the width of each rectangle is 1, so I'm going to factor that out. And now I'm going to start with the first right-hand data point, which is going to be the 25, and I'm going to add up all of these values. Okay, and so I'm going to start with 25 plus 30 plus 34 and so on, all the way to 50 this time. And when I add those up, I got 401 feet. Okay, but you can tell this is going to be an overestimate. And if we want a better estimate, we can just average those two. Okay, so that's what I'm going to do next, is just take the average of the right and the left hand sums. So I'm going to take 371 plus 401 all over 2. And I get 386 feet. Okay, now you can tell that this is a bit more accurate of an estimate, because if I look at the difference between these two, the overestimate and the underestimate, it's only a difference of what, 29 this time? Or 30? Yeah, 30 actually, because yeah, 371 plus 30 would be 401. So in this case, the difference is 30. So if this 368 is going to be right in the middle. So now this is going to be plus or minus 15 feet. All right, so we got a little better estimate. In the previous example, we had plus or minus 30 feet. So it's interesting that you sample the data twice as often and you get half the error. All right. So now these right and left-hand sums are called Riemann sums. Okay, these are called Riemann sums, and they are the basis for the integral, which is what we're going to talk about in the next section. Okay, so these are Riemann sums, and I'll write that down. Riemann, M-A-N-N, sums. Okay, and the idea is that if we, take we sample data more and more frequently, we break the intervals into finer and finer subintervals, that we're gonna get better and better approximations for the area under a curve. Okay, and so and if the velocity is positive, the total distance is the area under the curve. Okay, so so that's the idea. That's what we're going for here. So if we can find the exact area under the curve, then we've, especially if in this case where we're finding the area under the velocity curve, then we can get the exact distance. All right, so I'll meet you in the next video.